Welcome to another lecture for the 2004-2005 academic year. Thank you all for coming, and thank you especially to our distinguished lecturer of today, Edward Lee from the University of California at Berkeley. So he is the director of the Follow Me project and the director of the chess software and hybrid systems. And I was asking him about his books, so I can tell you about the books that he's written, and I knew of a couple of them, but then he went on to explain all the other books that he's written, and one of our colleagues here, Sugar Lactardia. So one colleague called the Green Book, right? And so he's an expert in digital communication, and like I said, embedded software, system modeling, and the Follow Me project, which he started with his advisor David Messerschmidt, is a modeling, simulation, and analysis and design tool for environment. And he has many honors to his credit, including the Presidential Investigator Award. He's a fellow of the IEEE. He has the Frederick Evans Furman Award for Engineering Education. And I've enjoyed the discussions that we've had over the last couple of days, and we've had quite a few people who've been very interested in learning from him. Everybody has enjoyed the discussion so far. And unfortunately, this is it. He's got to leave tomorrow morning back to Berkeley because he's taken on the position of chair of the electrical engineering division at Berkeley. So he's a very busy person, and it's hard to get too much of his time, but we're very appreciative of this day. So without further ado, let's begin.
Thanks. I'm going to try to speak loudly here, so if you can't hear me in the back at any point, just wave your hands furiously, and I'll do something. I was really delighted to see that that wonderful spread of food, because I was afraid, this is a big room. How are we going to get enough people here? Now I know. The secret is how to spread it. It's really fast. So I'm going to be talking today about some of the work that's going on in chess. And I'm actually one of 4 directors, not the director, but it's very much a collaborative project with Berkeley, Sanjay Vinchutelli, and with Tom Hensinger and with Shankar Sastry. And the focus of that effort is very much on, well, many different aspects of hybrid systems, which we actually, in the context of chess, define rather broadly. But in the context of this talk, I'll take a somewhat narrower definition and focus on the kinds of systems that mix the continuum of the physical world, physical dynamics in the physical world, with discrete transitions like what you find in software systems. And I think culturally, this study of hybrid systems, I think, has grown up as very much a collaboration between the control systems community and the computer science, particularly formal methods community. And it's interesting that I'm talking about it these days because I'm actually not in either community. I actually don't have much of a background in control systems or formal methods. But nonetheless, I guess I'm a bit of a dilettante, so I get my fingers in lots of things, and this is one of the things that I've gotten involved in recently. But I'm taking a stand on hybrid systems that I think is a little bit controversial and a little bit confrontational in both communities, which is, if you're a control systems person, what I'm going to say is that hybrid systems are not models of the physical world. They're programs in a programming language. And if you're a computer scientist, what I'm going to say is that programming languages are not just specifying transformations of bits, but they're actually describing system dynamics. And that we are interested in fact, using the properties of programming languages to be able to infer properties of that system dynamics. So in some sense, that sort of two-faced statement is what this chess center is all about. It's getting this computer science view together with this, with the what I would classify as sort of an electrical engineering systems view. So the idea here of hybrid systems as having an operational semantics, the title itself sort of suggests this tension between a programming languages view and a system modeling view. So I'll try to develop that out here. So the premise is that hybrid systems can be thought of as executable programs. And they need to be given an executable semantics. And of course, the big challenge in doing that is that the continuous dynamics of hybrid systems are not traditionally something that programming languages embrace very well at all. So the question is, how can you broaden the notion of a programming language so that it embraces these continuous dynamics? The corresponding thing, the converse, is that if you think of hybrid systems as, in fact, programs in a programming language, it turns out you come to different conclusions about how to deal with certain physical phenomena such as discontinuities. Okay, and I'm going to try to allude to those as I go. So just to set the stage, I think that the work that I've been talking about, that I'll be talking about, is in some ways very experimental. In my group, we build software, and we use the software as a way of kind of testing ideas. And we've been evolving over years what I would call a software laboratory, which is the Ptolemy system. And we use this laboratory as an infrastructure for building experiments. So one of the experiments we've done is to build a hybrid system modeling environment that's built on top of Ptolemy 2. We call it HiVisual. It's something you can download off the web, and it is very specialized. It's a domain-specific tool, specifically for modeling hybrid systems. This particular hybrid system model is, in fact, a description of a bouncing ball, which is a classic hybrid system that exhibits what's called a Zeno phenomenon. But you can see this chain of two integrators, which is simply a way of modeling a gravitational field. It's just F equals ma in pictures. Okay. The typical visual rendition for hybrid systems combines this kind of, if you're familiar with Simulant, this is sort of a Simulant style diagram of a continuous time system. That gets combined with something that is, in fact, a finite state machine, typically finite, although not always finite state machine. So these are states which represent modes of operation of the system. And it's this combination of the intrinsically discrete with the intrinsically continuous that makes these systems interesting. So, as an outline, I'm going to talk first about some of the implications that discontinuities have when you think of an executable semantics for hybrid systems. And then I'm going to talk about an idealization that in some sense sweeps under the rug the problem that is usually the first one people face when they talk about execution of hybrid systems, which is the numerical analysis problem. How do you numerically solve ordinary differential equations? I'm going to say it's a good problem. People have been working on it for 200 years. I'm really glad they've been working on it. Let's not talk about it any further. Okay? So in some sense, we can sort of state that, yeah, there's this problem, there's a family of solutions, but we can set it aside and focus on the other aspects of the problem. And I think that I'm going to describe what I call the ideal solver semantics, which is a way of getting us to that point where we can just set aside the numerical analysis problems. Choosing step sizes is a very practical issue. Discrete phases of execution is a way of coupling software behaviors with continuous systems. And then there's a whole bunch of miscellaneous issues that come up that I probably won't have time to deal with, but are there in case we get bored and decide to skip to that. Okay. So let me give a specific hybrid system example to be concrete. And instead of just showing PowerPoint exclusively, I'll show you an actual model in HiVisual of this system. So here we in fact have a model of a pair of masses on springs. All right, and I'm going to show an execution of this model, which will generate an animation in 3D at the upper right here, upper left. Sorry. So here you can see two masses on springs, and the dynamics of a single mass on a spring is a relatively straightforward thing. Okay, at least when idealized. But the interesting thing about this particular system is that these two masses might collide. And if they collide, they stick together for a period of time that actually depends on, there's an exponentially decaying stickiness. So let me just run this model again. Again, you can see the, so this is actually executing the program. The diagram that I showed is what I treat as the program. This is a animation that is generated as part of the program that's showing the dynamics of the system as it executes. Okay, this is not just a movie. And you saw here the two modes of operation. There's a separate mode and a together mode associated with this system. These are discrete modes, right? When the two masses are apart, we can describe the dynamics of the two masses in a fairly straightforward way. In fact, if I look inside of this separate state, I will see a Simulink style block diagram that has two second order, basically describes in pictures two second order differential equations. There's an integrator, there's another integrator, they're in a feedback loop. This feedback loop describes one of the masses on a spring. This other one describes the second mass on a spring. And then this zero crossing detector is looking at the positions of the two masses and determining when in fact they collide. And it generates a discrete event called touched that will trigger a mode transition to the together state, okay, which I can look inside of to see a description of the dynamics in the together state. So in the together state, again, I have a single second order differential equation that describes a single mass with two springs. Okay, so it's a slightly different equation, but not much different. And then there's a first order differential equation here that is generating an exponentially decaying stickiness. Okay, and then if I go back to the state machine, I'll see that in fact, let me see if I can zoom in on this. The transition from the together state to the separate state has a guard, which simply says that if the absolute value of the force exceeds the stickiness, I'm going to take this transition. So at that point, the stickiness has decayed sufficiently that the point masses come apart. Okay. This particular model, by the way, was inspired by a MEMS problem. Okay, MEMS accelerometers, which are actually widely deployed in airbag systems these days, have silicon fingers that are interleaved like this. Okay, and when you subject them to an acceleration, the spacing between the silicon fingers varies, and you can measure that changing in capacitance. If they are subjected to too much acceleration, they will collide, and they'll in fact stick together until their charges equalize, and then they come apart. So this was in fact constructed as a model of that kind of a MEMS system. So physical systems like that, MEMS systems, often exhibit this sort of hybrid behavior because there are these discrete mode transitions that are caused, for example, by discrete events like collisions of physical objects. But to me, actually, the most interesting thing about hybrid systems is that they give us a new way to talk about the interaction between software and physical systems. Because the software sort of intrinsically has these discrete mode transitions associated with it. And so I think that that's really a big part of the motivation for trying to think of hybrid systems as in fact programs in a programming language. So there's a diagram. We think of this diagram as a program. Now, you might say, well, no, it's not a program. It's a block diagram. Block diagrams aren't programs. I know that, right? How can you edit it in Emacs? You can always edit programs in Emacs. Well, not really. I mean, programs can have visual syntaxes, and it's an issue that we could probably argue endlessly, preferably over beer, about whether it's a good idea for programs to have visual syntaxes. It's kind of beside the point here. We have a tendency in our project to use visual syntaxes just to change the frame of reference. Because if we give you text, most people, if they're C++ programmers, read it as if it were C++. And we're trying to get you into a space of a very different kind of program. So it's very different in the sense that here we have four components in this program. These components are intrinsically concurrently executed. If you want to see concurrency in C++, it's much harder. Okay, it's hard to actually explicitly see the concurrency. Okay, so if we look at the structure of this, as I showed before, the description involves a combination of a finite state machine. This finite state machine has two interesting states, the separate and together states. And the transitions between states are annotated with guards and also actions that can be taken at the discrete time of these transitions. Okay? And the states themselves we find to describe the physical dynamics. So if I look, for example, at the dynamics of these two masses on springs, while they're separate, I simply have two second-order differential equations, which I can rewrite as integral equations, and it's really the picture that I showed with the two integrals is simply a very literal description of this integral equation. Okay? So the dynamics, while the two-point masses are together, is similarly describable as a second-order differential equation. Now, I want to point out the reason that I'm putting up these equations is that if you come from a control systems background or an EE systems theory background, this sort of equation is extremely familiar. And what are the objects that you're dealing with in these equations? Well, you're dealing with functions of time. Okay? So in this particular case, P is the position of the two-point masses. And it varies as a function of a time continuum. So I assume in this case that time is some subset of the real line. Okay? So the position as an object is this function of continuous time. Now that kind of a function is sort of intrinsically difficult for a computer to deal with, except perhaps symbolic. Because if it tries to represent it numerically, well, there's an uncountably infinite number of points that have to be represented, so that's kind of a problem with computers, so you don't try to represent it numerically. The usual formulation in a systems theoretic framework is you assume the timeline, let's call it T, is some connected subset of the reals. Okay? So in that case, the position is a function that maps that timeline into the reals. Okay? Because in this case, I've reduced the problem to a one-dimensional problem, so it's just the reals. And we can talk about things like the continuity of such signals. And we have a well-established theory for doing that. So it's nothing very sophisticated, except that there's some interesting points in hybrid systems where you have discontinuity. So in particular, P dot is the velocity of the point masses. It is also, velocity is also a function from the time continuum into the reals. I could plot that velocity as a function of time, and I'll see that the red mass and the blue mass have started out moving in opposite directions, with opposite velocities here. Then they come together and they collide, and then their velocities are forced to be the same. There's a point of discontinuity right there, and an interesting question comes up is, if you're thinking about this as a programming language, what semantics should you give to that discontinuity? Okay? And the answer is not the same as the answer you would give if you're working within the realm of differential equations, where you've got a bunch of mathematical tools for dealing with continuums and discontinuities on those continuums. So in particular, if we focus on that discontinuity, the question is, how do you deal with that discontinuity in software? Well, in software, any representation of these continuous waveforms that can be plotted is going to be, in fact, a countable set of points that is given as a function of, it's really given as a pair, a time-valued pair. Okay? The problem is that at this discontinuity, there's not one value, but actually multiple values of the signal. Now, if you're working in the space of differential equations, you just say, well, this is actually not a big deal. We just say that the velocity at that point is undefined, and you talk about limits from the left and the right. Okay? That's a relatively straightforward, established way of dealing with these kinds of discontinuities. It doesn't work in software, right? Because you no longer have the continuum, and consequently you can't talk about the limits. So the key question becomes, if you want a programming language semantics, how do you give an unambiguous meaning to the discontinuity? In other words, it's got to be a meaning in the program that is not the same as a rapidly varying continuous signal. Okay? It's got to be semantically distinguished. So the observation is that actually the form of the function, the velocity function, was not rich enough to express what I want to express. If I think of the velocity function as simply a map from a connected subset of the reals to the reals, that's not actually a good abstraction at all for the software world. So I augment the abstraction and I say, in fact, that any continuous function, x, continuous time function, is going to be a function of two things: the time continuum and an index, which is simply a value, a natural number. Okay? And this is going to allow a signal to have more than one value at a particular time. So t is still a connected subset of the reals, and it's the natural numbers. I change the form of the function. At each time t, the signal x has a sequence of values, not just one value. Okay? So let's explore the consequences of that a little bit. Let me do it in the context of a slightly simpler example than the point ones. So here's an example that has a finite state machine with two states, and it's a continuous time system that simply outputs piecewise constant values. So there's a constant output in each of the two refinement states. So regardless of which state you're in, the output of this modal model, as we call it, will be constant. But it's going to be two different constants depending on which state. Okay? So we can use this to implement a very simple scheme called hysteresis, which, if I look at a plot, looks like this. If I give it a sinusoidal input, what I want to do is I want to make a discrete transition when the red plot exceeds some threshold going up, and then I want to make a downward transition when it exceeds a different threshold going down. So in some ways, this is a relatively noise-insensitive way to detect zero crossings. Right? This could be a very noisy sinusoid, and the square wave will come out roughly the same. So hysteresis is kind of a standard way of giving you a certain amount of noise in it. Now the issue here is that at the point of the discontinuity, this blue signal, in fact, has two distinct values at a particular time. It is not correct in a software environment to approximate that like this, as a sequence of two distinct values at two distinct times. And the reason it's not correct is that this is semantically indistinguishable from a truly continuous signal that happens to be varying rapidly. So discontinuities are actually an intrinsically interesting thing. We want the semantics to be able to encapsulate them. We need to be able to have a signal formulation that allows multiple values at the same time. By the way, this idea has been bandied about in the semantics community for some time, programming language semantics. There's a term that's been applied to this kind of structure called superdense time. So in particular, Amir Noeli used that term superdense time because you've got denseness that the time continuum gives you, but then you've got this additional dimension thrown in on top. Okay. So what are the consequences? Well, one of the interesting things is that if you think of these continuous time functions as functions that map time across an index into some set of values, then it's possible, in fact, for a signal to have an infinite sequence of values at a particular time. Okay? So you could construct a program that, when it reaches a particular value of time, progresses through an infinite chain of values and never stops computing those values. And in a sense, that would prevent time from progressing from memory. Okay? We call that a chattering Zeno condition. Okay? It's chattering because, in a sense, there's no progression of time here. And we want to be able to ensure that particular systems are free of chattering Zeno conditions. So, in particular, what we mean by a signal not having a chattering Zeno condition is that we can find some integer m such that for all indexes greater than m, the value is constant. Okay? So in some sense, at each point in time, the signal settles to some value. Now, if you're looking at a signal like these, like the velocity of these point masses, most of the time it has only one value. It settles immediately. Okay? At the discontinuities, it has two values. It takes two steps to settle. Okay? If you think about arbitrary software involvement with physical systems, the actions of the software can be any terminating sequence of values at an instantaneous time. Why does it have to be at an instantaneous time? Because there's no time progression in the software semantics. Right? So the right model of it is that time doesn't advance while the software advances. Okay, so if you have a non-chattering signal, you can define a final value signal. A final value signal is simply the value that it settles on at each time. Now this is going to be an ordinary continuous time function. You can similarly define an initial value signal, which is simply the first value at each time. Again, an ordinary continuous time signal. Now you can define a notion of continuity for these signals on superdense time. So this signal is said to be continuous if it is a non-chattering signal, where the initial signal is continuous on the left, the final signal is continuous on the right, and the signal x has only one value except at a set d, okay, of values of time. The set d are the times at which the discontinuities occur, okay? Now we have to put some constraints on the times at which the discontinuities occur. If we allow discontinuities to occur at arbitrary times, right, then we could in fact have discontinuities occurring at all times, which would create a very difficult signal to work with. Okay? So we constrain this set D, in fact, to be a discrete set, which has a particular technical definition. And I won't go into the technical definition, but let me just say that it's not quite countable. Countable is not sufficient. Okay? It's not sufficient for the times at which the discontinuities occur to be countable, because then you could, for example, have a signal that was discontinuous at all rational times. But that would not be a very useful signal either. Okay. So discrete is a stronger condition than rational, and if you're interested, I can go into it later on. But let me instead move on. Yeah, question.
What about the usual math course definition of having finitely many jumps in any finite interval?
That turns out to be equivalent to discrete.
The way you meant it.
Yeah. So finitely many discontinuities in any interval. Okay. So the first issue that I addressed is that the classical EE systems formulation of a signal doesn't quite work in the software world. Right? The domain can't be just the dense time. We have to augment that in order to unambiguously deal with discontinuity. So that was the first departure from convention here. Now, the second is this issue of if I've got an ordinary differential equation describing the continuous evolution of some continuous time system, and I want to execute that on a computer, how do I do that? There are standard ways of doing it, of approximating the solution to an ordinary differential equation numerically on a computer. Okay? The software that does the approximating is called a solver. And the theory under which solvers are developed is very old, although it continues to make slow progress, at a relatively mature theory. I would like to say we can sweep that issue under the rug entirely with this notion of an ideal solver. Okay? So in particular, if I define, what do I mean? I've got some signal that's evolving continuously in time. Okay? Possibly with occasional discontinuities, although I haven't shown them here. Okay? I'm going to define a discrete trace, which is simply a set of values of the signal where the times occur on a discrete set. Okay? So again, finitely many times in any finite interval is sufficient. Okay? So the discrete trace is simply a set of values. It's in fact going to be a countable set, but it's, again, stronger than countable because the signal values can be ordered, totally ordered. Okay? So I have a sequence of signal values at discrete times. I call that a discrete trace. In the ideal solver semantics, all I need is for the time between two values of this signal that the ordinary differential equation that's governing the dynamics have a unique solution. Okay? Notice all I care about is that it have a unique solution. I don't actually care about how I find that solution. That's how I sweep the issue of the solver under the rug. I say if it has a unique solution, I've got a well-defined discrete trace for this signal. Okay? And that's not actually so far-fetched. In fact, if you look at the point masses example, the masses on springs example, I can actually solve those differential equations symbolically. Okay? And consequently, I could choose discrete points in time and write down, assuming I had infinite precision arithmetic, which of course I don't, but if I did, I could actually calculate the solutions to whatever precision my arithmetic can deliver using those symbolic solutions. So that would be, in a sense, the ideal solver. The ideal solver kind of says, well, suppose you can solve the ODE symbolically, you can define the solution. The solution is uniquely defined. As long as that solution is uniquely defined, then you can define what a discrete trace of a signal is. Okay? So this ideal solver semantics, the idea is that it gets us away from this problem of how you actually go about numerically doing the solving. But of course, you can't completely do that, right? If you're going to execute this thing in a computer, in the case of the masses on springs, I was able to solve the ordinary differential equation symbolically, but there's a lot of systems for which I can't do that. So this is one of my favorite examples. It's a simple third-order nonlinear differential equation that exhibits chaotic behavior. Okay, this is a phase space plot. So it's a plot of one of these signals versus another one of the signals. Okay, and you get these weird sort of patterns. It's called a strange attractor because it tends to orbit around this, and then at sort of unpredictable points in time, it switches and starts orbiting around this. And then at unpredictable points in time, it switches back and starts orbiting around this. Each of these points is called an attractor. This kind of an ODE is hard to solve symbolically, and it's so you're sort of stuck with numerical techniques. Now let's look at the structure of this kind of a system. Okay, so this diagram that I gave was actually the program. It had a bank of integrators here, which I will simply abstract as a single integrator with vector value inputs and outputs. Okay, just collapse the bank of integrators into one integrator. And the integrator is coupled in a feedback loop with a function. And the structure of the differential equation then is simply that the derivative of x at time t is this function evaluated at the current state of the integrator, x of t, which is the output of this box, and possibly taking into account the current time. So you can allow for time-varying behavior in these systems. Okay, so this is actually, a pretty useful general structure. Integrators and feedback loops with functions that give me the derivative as a function of the current state. So this is the basic abstraction for this, for a class of ordinary differential equations. Now, suppose that I take this class to be the class of systems that I'm going to define in my programming language. Then a key question, whenever you define a programming language, you're interested in how expressive is the programming language. Does it cover a sufficient set of systems of interest to actually be useful? So the question for this becomes, is this formulation in fact sufficiently general? Now, the first thing I can do is ask the question, well, can I apply the ideal solver semantics to some program that's given in this formulation? And the answer is yes. There's some well-known sufficient conditions on this function f. Okay? They're sufficient conditions. They're not necessarily sufficient. Okay? But they're sufficient conditions to guarantee uniqueness of the solution to the differential equation over sufficiently small intervals of time. That's all I need to apply this ideal solver semantics. Is that these sufficient conditions on this function be satisfied. Okay, now, I can use this ideal solver semantic, but it's kind of an idealization. What happens when I actually go and try to execute this program? Well, in fact, it's not uncommon in programming languages to realize that an execution of a program is actually an approximation of its semantics. We know that whenever we have programs that do arithmetic. Okay? The arithmetic is actually, in some sense, the semantics of multiplication is idealized. When you write the program, multiplication is just multiplication. When the program gets executed, the multiplication is actually an approximation of multiplication. It's not actually multiplication. Okay? The question is, when is that approximation good enough? Well, the same question is going to apply to solving these ODEs. Is that you're going to have an execution that's an approximation, and when is that approximation good enough? Yeah.
Isn't this assuming, or isn't this depending on the actual physical implementation of the computer that you would use?
Yeah, absolutely. So I mean, one solution would be, I could say, well, no, let's take literally the ideal solver semantics, and I'm going to want to execute that, in which case I better use an analog computer. Okay? Analog computer is going to have a hard time with the discrete mode transitions. Okay? So the leap that I'm taking is I'm going to say, no, actually, digital computers are good enough for this. Okay? I can assume that my underlying implementation falls within the realm of the computer, in the sense that we mean it today as something that can be executed by a digital computer. That's what the ideal solver semantics gives me, is that ability to say, no, I can actually compute this thing. But now I'm going to say, well, just as with multiplication, I actually have to approximate it. How should I approximate it? Okay. So a key question becomes, how do you choose the discrete points in time where you're going to represent this signal? So in particular, this ideal solver semantics says that if I have a sufficiently small interval, and my function in the feedback loop satisfies certain sufficient conditions, then the solution is unique. Okay? What is a sufficiently small interval of time? Well, in fact, in practice, what people do is they adapt the step size that is used in solving the ordinary differential equation by looking at the dynamics of the signal. Okay? So there's actually several different criteria that we have to apply that are going to determine the points in time at which I have to represent the values of the signal. One is that at any point of discontinuity in the signal, I have to represent the signal. Okay? Otherwise, I will fail to represent that discontinuity. So I constrain it so that the points of discontinuity are assured of being in my set of time values at which I represent the signal. At this point of discontinuity, the signal will have more than one value out of the sequence. So that's okay. Okay? But then I have unpredictable events, such as in the case of the masses on springs example, the point in time at which they collide. Okay? The positions are not discontinuous. Okay? But the velocities are. And it's very hard if you're just looking at analytically the system to determine exactly at what point in time these things will occur. So if you're doing this numerically, okay, then the way that you identify the points in time at which threshold crossings occur is in fact by missing them. You calculate a point in a signal. You calculate a second point in the signal, and you discover that you've crossed a threshold. Okay? At that point now, the typical technique is you backtrack. Okay, so reverse time, and you say, uh-oh, I missed an event here that was an important event. Okay? I better throw out my solution at this point in time. Backtrack the solution until I identify the interesting point in time, which is the point in time at which this event occurred. Okay? So that's a technique that's used for identifying these interesting events. And in fact, that's the technique that's used for identifying the time at which these balls collide. So the solver will in fact precisely identify the time at which they collide. It's not just a discrete time approximation. A discrete time approximation would actually allow the balls to infringe on one another, right? Which they don't do. And then the third criterion is that we have to make the step sizes sufficiently small so that if the dynamics of the system is such that that I need more points in the solution, then I have to sometimes also backtrack and redo the solution with smaller step size.
Why when I do backtrack, do I have to find a point? I don't get to find a point. I don't need to run what I do.
Yeah, in fact, one of the questions when you're identifying threshold crossings like this is to what precision do you want to identify, right? That depends on a number of semantic issues. At what precision are you representing time? Okay. How is time represented in your execution sequence? You have to decide, right? And you may say that, well, I in fact I want to identify the point at which it is embedded to the resolution in which I'm representing time. That would be a legitimate semantic definition, and it is computable.
That's part of the response.
That's part of the semantics, and when you specify a language, you have to specify that as part of it. Okay. Here's what a typical practical solver looks like. This is a fairly popular technique for solving ordinary differential equations numerically. It's called the Runge-Kutta 2-3 solver, or RK2-3 to its friends. Okay? And this uses the structure that I showed before, where there's a function that, given the current state of the iterators and the current time, will give you the derivative, okay, of the function. That's what it does. It gives you the derivative. So in RK2-3, we actually calculate the derivative by evaluating that function. Then we estimate the derivative at half of the step size. So h is the step size, my current best guess on a reasonable step size. Okay, that's actually what it is. So I estimate the derivative at half the step size, 3/4 of the step size, and then I do something that is incredibly ad hoc. I estimate the the value of the signal at the next time step, which is the current time step plus the step size, to be this point combination of the original signal and the step size multiplied by the derivative estimates. Okay? So we won't go into why this is, right? But there's interesting properties about this. One of them is that this, in fact, requires an evaluation of this function f at 3 different times with 3 different inputs. Right? It requires the evaluation of the function with the current state as an input, an estimate of the state at half the step size, okay, an estimate of the state at 3/4 of the step size. So if you think of about this from a programming language perspective, this is a little bit weird, because if I specify the function, if I specify this function as simply, a piece of sequential code, procedure, okay, and I'm going to evaluate that sequential code each of these 3 times with these 3 different arguments, then I better be damn sure that procedure has no side effects, okay? Because if it has any side effects, I'm dead, right? The solver, in fact, in evaluating it 3 times is going to get extremely unpredictable results. As a consequence, I have to be able to specify the components that give that function in such a way that there is a way to evaluate them without side effects. That has profound consequences on the programming language. It means these cannot be arbitrary chunks of software. They have to be constrained so that they can, in fact, be evaluated without side effects. So side effects are where a procedure changes the value of some variable that is persistently visible after the procedure returns. So this is the overall structure, but now in software, if I'm going to define this function in software, I have to do so in such a way that I am able to evaluate that function without side effects. Now, an interesting question then becomes, actually let me skip over the adjustment and step size issue. It's sort of an interesting issue that step sizes get adjusted dynamically in these solvers. And they do it by looking at, in some sense, how quickly the signal is wiggling. If it's wiggling too fast, that'll reduce its step size. Okay? And this is a criterion that's used. It's actually a high-pass filter on the derivative. the derivative is varying rapidly over one step, then your step is too big. Okay. That's all it does. So a consequence of that, of course, is that I may in fact, in executing this program, I choose a step size, I evaluate this function 3 times, okay? In the process, while I'm evaluating it 3 times, I get estimates of the derivatives at those at 3 points in time. I look at how much it's wiggling, and then decide whether my step size was sufficiently small, okay? So I may have to throw out that calculation and redo the calculation of a smaller step size. Again, that reinforces that the software that evaluates this function had better be free of side effects. Because if in the process of doing that evaluation, I left behind a change in state of the system, then when I come back and redo the calculation with a smaller step size, the system has changed state, the function that you evaluate is different, and as a consequence, that won't work.
How does that match with often having multiple values in any given time?
Yeah, so the multiple, so this is really dealing with the progression in time between points of discontinuity. Okay, so at the points of discontinuity, you actually progress through a sequence of values. Okay, that's it's you separate these phases of execution in a sense between these discrete and continuous phases. So this is really just dealing with the continuous phase. So given that this function has to satisfy certain properties. Well, first of all, I mean, in a sense, mathematically, we've got a good description of what we need from this component. If you think of this as a software component, what do we need? We need it to be a function. In fact, literally, right, in the mathematical sense, a function, which, given the current state and the current time, yields a derivative. Okay? And the fact that it's a function means intrinsically that it's free of side effects. Right? Mathematical functions don't have side effects. So the question is, if I build a software framework, a programming language where I can specify those functions, how expressive is that length? So if I look at this feedback system, there's certain things that might be kind of troubling. Perhaps not all differential equations fit this framework. So for example, suppose I don't actually have feedback, right? Suppose I have some signal source that gets integrated and then some signal sink that produces a plot. Okay. That's a fairly common scenario. But that actually fits within this mathematical framework perfectly well, because I can, in fact, define a function here. It happens to be a rather trivial function because it ignores the value of x to produce the output. The output is, in fact, going to be only a function of time. But it's still a function, so it fits the framework, so I can do it. So that falls within my expressiveness. I can express such systems. What about systems with external inputs? I mean, this closed feedback system seems to suggest there's no way to get inputs from the outside world. Well, actually, there's inputs from the outside world. Well, those are just signals that vary with time. Okay? So here's a function, okay, that combines a signal that varies with time in some way with this value of x to produce a current x dot. Okay? It's still a function. It still fits within the framework. Okay? The constraint for no side effects does not prevent me from having external inputs. What about state machines? Okay? And here's where I get to wanting to mix in the discrete behavior. And all of a sudden, I realize, actually, no, this function can't be a state machine, not a mediator. Right? State machines sort of intrinsically have side effects. They have state. And an evaluation, in some sense, can take me, can cause me to progress from one state to another. So I have to have some way of evaluating a state machine that prevents me from progressing from one state to another when I don't want to progress from one state to another, and over which I can then exercise control and actually progress to the next state only when I'm ready to commit, when I get determined that there's no more backtracking needed. Okay? So that requires me to construct the software in a somewhat different way. I can't simply give a single procedure. Okay? So in particular, if I want to represent this function in a box that has just a function implemented as a procedure, that's not sufficient. Why? Because if it's a function, it can't have side effects. And if it's a state machine, it has to have side effects. Okay? So I can't reconcile it. So as a consequence, I have to define the component using at least two procedures. One of which is a function that given inputs produces output, and another one of which gives me a new state. Okay? So we call this a stateful actor, and this is simply characterized by a pair of functions. A function f, that is exactly what we had before, given an input, it gives me an output, has no side effects. And a function g, that given the current state, the current input, and the current time, gives me a new state. Okay? The function f, by the way, we also augmented so that it has available the current state. So consequently, I can get the modal behavior this way. This function, given the current state, the current input, and the current time, gives me the current output. No side effects. This function, given the current state, current input, and current time, gives me the new state. Okay? The new state, if I commit that, take that to be the new state, that is side effects. That's what we mean by side effects. So I have to be able to separate the software into these two pieces. Okay? I cannot define these components using a single procedure only. It turns out this is sufficient to support unpredictable breakpoints and step size adaptation. As long as I can define the components using these two separate procedures, one of which is side effect free and the other one of which is not, then I'm okay. In programming languages, a key question that often comes up is your language composition? Okay? And what this means is that languages provide an abstraction mechanism. So most of the programming languages that we use provide procedures as the basic abstraction mechanism. And procedures can invoke other procedures. And you can aggregate a sequence of procedure invocations within a procedure. It's a nice compositional framework, right? I can define procedures out of other procedures. So the same question comes up with this hybrid system formulation. Could I take one of these feedback systems and, in fact, use it as the definition of a component within another hybrid system formulation? Okay? And again, the answer is yes, sort of. Okay? But there's real difficult corner cases. This is clearly going to be a state machine. It's got integrators in it. Okay? So it's a state machine. So at a minimum, I know that I'm going to have to separate it into these two functions, right? One that commits state, one that doesn't commit state. However, if I try to do that with practical solvers, it turns out that's not quite enough. Because in the RK23 solver, I have to speculatively execute more than one step into the future before I can determine whether my step size was sufficiently small. Okay? In order to speculatively execute more than one step into the future, I have to commit to state changes, but I have to be able to backtrack out of those state changes later. Okay? Or I fail to get the ability to, I fail to get the semantics that I need. All right? So as a consequence, you have to be really careful composing these hybrid system models. In fact, we did it wrong the first time, and in the version of the high visual system that we released about a year ago, one of my students discovered fairly recently an interesting phenomenon. He constructed a very simple continuous time system. There's actually no hybrid dynamics. Two integrators in a feedback loop. And the bottom model is actually exactly the same as the top model, except that there's a hierarchy here. Okay? So I tried to encapsulate this integrator within a component definition. Okay? Now ideally, this would simply behave as an integrator. Right? So the bottom system and the top system should behave identically. They did. Okay? The mere encapsulation of this, it's as if in a procedural language. You know, you're writing a procedure, gets too big. So you take a subset of the code and factor it out into a new procedure. And ideally that doesn't change the behavior. You would kind of expect the same thing here. If I add hierarchy, that's just factoring out a component of the system. It shouldn't change the behavior. And it did change the behavior because we had not correctly handled the backtracking of state across these solvers, across layers of the hierarchy. So this, in fact, when you execute this system in high visual, it in fact uses two distinct solvers that have to cooperate in some sense, preferably with minimal amount of information exchange. Okay, but they cooperate in some sense, and you have to define the semantics of that cooperation. So anyway, it turned out to be a harder problem than we thought. Okay, so let's talk about discrete phase of execution. So here's a real simple example of a system that is trying to combine software and continuous physical world together. And the idea is that I have a state machine that is going to progress through a sequence of states in 0 time. Okay? In fact, if you look at the guards on these state transitions, they're always true. So when I enter this state, the outgoing guard is immediately true, so I'll immediately take a state transition. Here, the outgoing guard is immediately true. I again take a state transition, and so on. So semantically, what we would like this to mean is that at a certain time I take this transition, then without advancing time, I progress through a sequence of states. It's as if I'm modeling the execution of software and using the usual software abstraction that computation doesn't actually take time. Okay? So a trace of the system should look like this. So in this particular case, I've shown the discrete points that are being calculated by the solver. At this point, I hit the threshold where this guard becomes true. I progress to this state. Then I progress to a sequence of states, which is representing some software calculation. So this is going to be a sequence of states. And then I settle into a state where I produce a constant value. Okay. And these guys here are simply looking for threshold crossings. And one of the things that we're interested in is, in fact, being able to determine that the sequence of states, despite the fact that it took 0 time to progress through this sequence of states, that the signal did, in fact, cross these thresholds. Okay? There's a lot of hybrid system solvers, execution software that won't, in fact, do that correctly. The other thing that's interesting about this sequence of values in 0 time is that if you integrate it, it should have no effect, right? Mathematically, that's what you would expect. If you have a signal that's 0 everywhere, okay, except at time 1, where its value is 1. What's the interval of that signal? Well, 0, right? The value at time 1 is irrelevant. Okay? It still integrates to 0. So you have to ensure, in fact, that your execution semantics obeys that. This demonstrates that. I integrate this signal up here, I get this nice smooth curve, and then I switch to a straight line and continue to integrate. And the sequence of values has no effect on the integration. That's an important part of the semantics of the language. Okay? This part of the semantics of the language is not met by any other hybrid system execution environment that we know of. Simulink is a popular one, for example. You can construct a Simulink state flow diagram that has the same semantics. It progresses through a sequence of states in 0 time. But in fact, in Simulink, it doesn't do it in 0 time. And in fact, the time over which it holds the value is completely solver dependent. It's not something that's specified at all in the program. Okay? As a consequence, there is non-trivial behavior in the program that is not specified in the program. And this is not just numerical approximation error. This is a semantic error. Okay, so discrete phases of execution. I raised the issue of chattering Zeno conditions, and as I predicted, I don't really have time to I don't want to keep everyone here, but let me just pick one of these miscellaneous issues, right, which is Zeno behavior. I mentioned chattering Zeno. Chattering Zeno is where a signal acquires an infinite sequence of values at a particular time. There's another form of Zeno signals that can arise in hybrid systems, where time does actually advance, but it advances ever more slowly. Okay? So this is a signal where, this is an example of a Zeno system where I'm getting, in fact, an infinite number of events in a finite amount of time. And the time between events is non-zero, always non-zero, but it's decreasing. Okay? The classic favorite example in the hybrid systems community is a bouncing ball example. When I idealize a bouncing ball, time between bounces gets arbitrarily small, okay, but it never goes to zero. And if you're doing any numerical execution of that, it has to capture each collision with the surface, each discrete event. That exhibits this Zeno behavior, okay, and time fails to advance past the Zeno condition. So one of the interesting questions that comes up in the hybrid system community, and treating this as a programming language, is that is there some way to do static analysis on a program that determines whether it has Zeno conditions? In the case of chattering Zeno, it really depends on how rich your language is for specifying your mode transitions, your state machine language. Okay? If your state machine language is Turing complete, then static analysis won't do it. Okay? It's equivalent to the halting problem. It turns out that you can also apply similar criteria for the continuous part, and you can come up with conditions under which Zeno conditions can be avoided. And there are certain, at least conservative static checks that for certain systems will prove that they're true Zeno conditions. Okay, I'm going to just summarize with what I've said. So the first observation I made was that signals, if we're going to talk about execution of hybrid systems, have to be able to have multiple values at a time. This changes the formalism that the EE-style systems folks have to use. Okay? And it's a non-trivial change, but it's a manageable change. There's a way to map this signal structure onto the conventional signal structure that people are used to. The second thing is that actors have to, in fact, you have to split the specification of components into something that is free of side effects and something that commits to state changes. The split is intrinsically required by the semantics of hybrid systems. There's no way to avoid it. So any programming language for hybrid systems is going to have a way of doing this separation. The third thing is that compositionality is a really tricky problem in these hybrid system languages. That you'd like to be able to take an arbitrary hybrid system and treat that as a component in another hybrid system. But doing that right is non-trivial.